Our last speaker before coffee break is Yannick Le Goc. I hope it was pronounced correctly. He's a software engineer. He worked 2 years in a public laboratory specialized in 3D graphics. Then after some projects in industry, he started to work for the Institut Laue-Longchamp in the instrument control service, and where he is currently developing the control software and other related tools. In parallel, and he is also doing other research work on the multi-methods concept. Please.
Okay, thank you for the introduction. Hello, everybody. So today I present you a new and original project that is called Nomad 3D, and we started it this year at the ILL. So, quick outline. So first I will introduce the project, then we'll see Nomad and SolidWorks, and the workflow in details, and then I will finish with 2 videos of demonstrations and a conclusion. So let's begin with a photo of the figure instrument that can be a user point of view. All you can see is walls and cables. So what is interesting for science is not there, it's inside. So we can put some webcams, but they will be set at some fixed points of view. So the idea of the project is to provide a 3D dynamic representation of an instrument so that we can augment the reality of the user of the instrument by providing him to see behind the walls. So in fact, our goal is to animate a 3D model in real time. So what do we have? We have Nomad, which is the instrument control software at the ILL, and we have some SolidWorks static models. And the idea is to mix both of them to obtain what? To obtain a dynamic 3D models. And this is the goal of the project, which is called Nomad 3D. So quickly, what is Nomad? Nomad is the instrument control software at the ILL. We control more than 35 instruments. And for the axis part, Nomad is sending some motion requests to the electronics card, which control the axis. And Nomad is permanently refreshing the encoder, or reading the encoder position by the electronics card. So we have a monitoring of the real position of the axis. On the other hand, we have SolidWorks model. So SolidWorks, for those who know what it is, it's a computer-aided design software for which the models are hierarchy of components, and the leaves of these components, I mean the last parts of the hierarchy, are the geometries, and these geometries are combination of basic shapes that can be prism, cylinders, spheres, and this combination are addition or subtraction. And I gave an example where you can see on the left a black cuboid for which we have some red spheres, and the subtraction of the red spheres to the cuboid gives this. So let's see an example of SolidWorks. So we have a beautiful goniometer taken from the HMD instrument. So this is just a part of the instrument. And you can see that it is very detailed. So we have the screws here, for example. And on the left, you can see all the hierarchy of the components. And you can see that it is very detailed. So the problem is SolidWorks models are not adapted to our goal because the combination of shapes is not loadable as is. Usually we have to load some sets of triangles and not sets of combination of shapes. And they are also too big, in fact. And moreover, some information are missing, and these information are the motion characteristics, for example, the 3D direction vector of the axis and the information of the walls. So, if we will find the goals of Nomad 3D, we need to transform a SolidWorks model into a standard Nomad 3D model, and we want to have a real-time display and animation of this model according to the physical axis quantities. So let's get into the details with our workflow. So first we begin with a SolidWorks model. Then we have the first application that we call the exporter, which is a SolidWorks add-in, and the main goal is to transform the combination of shapes into a set of triangles. And we also have the export function where we export some different files that we will be able to load after that. And this add-in is written in C# to access to the full API of SolidWorks. Then we have a converter written in Java So in this part, we need to do some cleanup of the geometries, for example, to remove some double vertices and invert some triangles. And we also have the level of details. And the level of details, the basic idea is to provide different versions of the models, from the most detailed to the coarsest, so that we can have an optimized rendering. And for all this operation, we use Blender with all its geometry algorithms. Then we have the editor. So the two last applications were automatic. We were given some parameters and we had the results. So the editor, now we have to edit manually the model because we need to enrich the model by the motion characteristics and the walls. And this application is written in JavaFX, and you can see now an example of JavaFX with 3D. So here is a Goniometer model where we can turn around like in SolidWorks. And now you can see that we removed the screws. They are not there because it's too small and we don't need it. Now you see the most detailed version of the model. And I will show you then the decimated version of the model, which has twice as less triangles. And we also have the convex hull version, which has 10 times fewer triangles. So it has a different aspect. So let's get back to the most detailed version. So on the left, you can see also the hierarchy of components. And what we can do on the graphical interface, we can select one by one the components just by clicking on the model. And we can also select an entire group of components by selecting on the menu. And now we can see that there is an axis already defined for this set of components, and you can see the direction vector here. What I want to do is to edit this axis and to change it from rotation to a translation. So it appears now in yellow, and we just position better the model. We can change the direction with the mouse, and then we position it to check that it is really a translation. So you see now the movement is different. So we set it at a convenient position, and now we will do what we call the calibration, so that we need to set the zero of the axis. So we just set median, zero or median position. Now we have that. We can map this axis to the real axis of Nomad. So we have access to the list of axes in Nomad, and we take the one that is called S2T. Okay, so next you can see the full model of the Figaro instrument. And what we want to do here is just to tag the walls. So it's a very simple operation. We just select one by one the set of components that we interpret as walls. And we just then have to mark them as walls in a menu above here. Okay, so now we are ready for the two final videos. So I will show you the view application for the Figaro instrument. And first video, we start with a point of view that looks like the first one for the photo, but now I'll let you with this psychedelic experience where you go literally through the walls. And we go directly to what is interesting us, in fact, because walls are not interesting, of course. So we are going directly to the sample table of the Figaro instrument. All these movements were realized with the mouse. So now on the right, you see the real movements that we recorded with a camera on the right. And you can see a vertical movement, of course, which is the most simple. There is another movement that is more difficult to see, but is a flipping. So you can see that it's doing like this. And there is another movement here. There is another part that is falling down, and you can see it here. So we have, in fact, 3 axes moving here. Here, we recorded the real positions of the sample table, and we injected them in our 3D model to obtain this movement. And you can see that movements are very close, and at the eye, for us, they are equivalent. Now we change the point of view where we are on the detector. So on the upper right, you can see the real detector view. So, but this time we break the walls because we don't need them, and the user can do what he wants. He's totally free during the movements. He can turn around the model, he can zoom in, zoom out, go above. He's totally free. This viewer application, we wrote it in 3.js. It is a 3D engine based on JavaScript and based, in fact, on WebGL. And WebGL is the OpenGL ES implementation in browsers. And we chose this library because it offers the best compromise between portability and performance. And so you can see the end of the movement. The detector is slowly arriving at the uppermost position. So we arrive at the conclusion. So Figaro was our first instrument that we converted with our tools. So we are testing it now with some users, and we are waiting for their feedback, and we'll prepare to the next instrument. In the future developments, we will soon develop a collision detection strategy, because some instruments at the air require to check the full trajectories of the instrument. Some movable parts can collide with the walls or can collide themselves too. So this is a very important algorithm, but there are some different strategies, and it's not so trivial to realize. Then we want also to be able to insert some movable and free objects, for example, some cryostats that can be big and then can also collide with some other parts of the instrument. And then we also integrate this code into the web application. It will be easy because our client is already in JavaScript in some tablet, and we want to integrate some augmented reality device, for example, Google Glass, or for more immersion experience, for example, Oculus Rift. So I think that you understood that transforming a SolidWorks model into a loadable and animatable model is not an easy task. So don't hesitate to contact me if you want to introduce 3D in your center. The project is open source and which has a EUPL license. Thank you.
We are a bit behind schedule, so maybe have time for one quick question. Otherwise, maybe there's also time the coffee break. But over there, I guess it's more. Oh, it's there. Okay.
Thank you for the presentation. What is the format of the file you are using to load your SolidWorks models in Blender?
In fact, we export the SolidWorks model into our own file formats, and there are two types of files. There is an XML file that is just describes the hierarchy of components, and we have some STL files that are the binaries that describe the geometries, so the set of triangles.
Okay, maybe a last one.
Yeah.
Have you perhaps considered the possibility of using VRML?
You mean for the last part, for the viewer part, because the main task of the project is to transform the model. No, because I think it's quite old for me, and 3.js offers very, very great performance. And you can go to the 3.js website and we see the examples, and you will see that you can run some very good OpenGL programs on the web.
Thank you.